So the figure above shows the graph of f prime, which is the derivative of the twice differentiable function f on the interval from -3 to 4. Now, they say it's twice differentiable because we're going to need our second derivative after a while, right? They just want you to know that the derivative exists, clearly. They showed us the graph of it. And also the second derivative exists. And it is twice differentiable on that interval from -3 to 4. So the graph of f prime has horizontal tangents at x equals -1, 1, and 3. The areas of the regions bound by the x-axis and the graph of f prime in the only intervals from -2 to 1 and 1 to 4 are 9 and 12 respectively. Respectively means in that order. So the area between -2 and 1, between the graph and the x-axis, is 9. Now notice it's not -9. They just said 9, and that's okay, because later on when we're computing it, we might get a negative depending on the direction we're going. But the actual area, like real world, can't be a negative area, is 9, and that one is 12. So part A, find all x coordinates at which f has a relative maximum. Give a reason for your answer. So let's think about this logically. Maximums and minimums occur where the derivative equals 0, or where the derivative doesn't exist. Well, it's always differentiable, right? So we don't have to worry about that. And also at the endpoints of an interval, I'm going to hold that thought till the very end, right? I'm going to just go ahead and deal with where the derivative equals 0. So here goes, number 5, part A. Straighten out my papers here. Here goes. Number 5, part A. Find the x coordinates at which f has a relative maximum. So I'm going to consider these points. I'm going to consider -2, +1, and 4. Okay? So as I consider that, I'm looking at the graph of the derivative. And so I'm thinking, well, f prime of x equals 0 at x equals -2. This is my mathematical doodling here, okay? This may not be my final answer. And then also at 1 and also at 4. Okay, so I'm looking for a maximum. Now, if you're looking for a maximum, you might be like, oh, there it's 1. No. Maximum of the graph. This is the derivative. So my graph is going from, original graph, f, is going from increasing to decreasing. Now, notice I pointed at positive derivative to negative derivative. So at -2, it goes from increasing to decreasing. Let's visualize that. It's going up, then down. So -2 is a maximum. I'm going to go ahead and write that. So there is a relative maximum. F has a relative maximum. I'm using the word relative because that's what they asked. Relative means maybe not the highest, but it's the highest in its little area. It's a rough definition. Relative maximum at x equals 2. Oop, -2, sorry. Why? Now, we need to justify our answer. They said give a reason for your answer. Because f prime changes from positive to negative at x equals -2. Maybe we're done, maybe we're not. Okay, let's keep thinking. What about this one? All right, so derivative is positive, negative, negative, negative. Well, if I go from negative to negative derivative, that means I'm going from decreasing to decreasing on my original function, so it's just continuing to go down. So I never reached a maximum. And then here, it was still negative. Now you might be like, oh, the graph's going up. Whatever. The graph is the graph of the derivative. The derivative is the slope. My graph here is negative, meaning it is decreased. F, original function is, I shouldn't use the word it. The original function, f, is decreasing leading up to 4. So therefore, it's going down, and so 4 cannot be a maximum. So we're done. Now, I did say one other little thing. Maximums and minimums occur at the endpoints of intervals as well. So like -3 is a possibility and 4 is a possibility. Well, we just ruled out 4. So let's think about -3. -3 is not an answer. And the reason it's not is because my graph is increasing starting at -3. So it goes up from -3 and then begins to turn downward. So if I start at an x value of -3, I don't know where exactly it starts on the original graph, but if I started at some y value and then went up from there, increasing, then it would not be a maximum. So we kind of ruled that one out without having to write anything. We've answered the question that they wanted us to answer. Okay, part B. On what open intervals contained from -3 to 4, notice they didn't include -3 and +4, is the graph of f both concave down and decreasing? Give a reason for your answer. Okay, so when I did this one myself and worked through it, I first looked to see where it was concave down, and then I looked to see where it was decreasing, and then I found the overlap. So let's do that. Let's go back up here. Where is it concave down? So I'm writing. You can't see what I'm writing, but f of x is concave down, or downward, on what intervals? So f of x is concave down on, let's see, concave down means the derivative is decreasing, okay? So here goes. I'm looking at the derivative, and if it's concave down, then the derivative is going down. That means from -3 to -1, and from 1 to 3. So -3 to -1, and 1 to 3. And maybe this is an unnecessary thought process for you, but it helped me, okay? I also want to know where it's decreasing. So f of x is decreasing. Is this my final answer? No, because I need to really put the two together. On, okay, what intervals? Well, a function is decreasing where its derivative is negative. So from -2 all the way to 4, and we could argue about whether 1 should be included in that or not, but let's just go ahead and put it. So -2 to 4, they won't count off for that. It's decreasing from -2 to 4. Now, let's find out where they overlap. So my thought process has led me to this. I want a derivative that's negative, so I'm looking just at the stuff. And I also want a derivative that's going downward, so I'm looking here and here. And maybe you jumped there immediately when you were thinking of this, but maybe not. So hopefully this thought process helped. If it was a waste of your time, I apologize. So f is both concave down and decreasing on the interval from, it's going down and it's negative from -2 to -1, -2 to -1, and we could argue that it's, well, I was about to say something that would be confusing, so never mind. And from 1 to 3. 1 to 3. There we go. There's part B. Let's do part C. Oh, wait. Let's not do part C. It said give a reason for your answer, and I have not. So I have answered with the intervals, but I didn't give a reason for my answer. And so let's do it. What were we looking at? You erase or white out this period right here. F of x is both the concave down and decreasing. So what were we looking at? Well, let me tell you. Because f prime is what? What were we looking for? We wanted it to be negative, okay? Is negative. And what else were we looking for? What were the conditions that had to be met for these intervals? They had to be negative and they had to be going down. So negative and decreasing on these intervals. I've not yet shown you how they're scoring this one. I'll go back to it in a minute. All right, here's part C. Find the x-coordinates of all points of inflection for the graph of f. Give a reason for your answer. Okay, here goes. A point of inflection is where your derivative ceases to increase and begins to decrease, or ceases to decrease and begins to increase. Okay, your derivative is changing directions. So here goes. F of x has a point of inflection at, and then we'll stop and we'll look at the graph. A point of inflection is a second derivative issue, meaning I need to think about the slope of this. And my slope is negative, then it's positive, then it's negative, then it's positive. And so I have a point of inflection here, here, here. So -1, 1, and 3. How do I know exactly it's those? That's why they told me this, that I have horizontal tangents there. Okay? So f of x has a point of inflection at x equals -1, x equals +1, and x equals 3. Why? Because it is at these x values, at these points, that f prime of x changes. You could say changes direction. I want to be really specific here. Changes from increasing to decreasing, or decreasing to increasing. Here goes, part D. Now it gets tricky. Now, they told you some stuff earlier. They said, you know, this area is 9, this area is 12. Now, what are you going to do about it? Well, let's find out. Given that f of 1 equals 3, write an expression for f of x that involves the integral. I'm going to not even read the rest of it. Let's just deal with that later. Given that f of 1 equals 3. Now, don't look at this graph and say, no, f of 1 equals 0. This is the derivative, okay? So f of 1 equals 3. Write an expression for f of x that involves an integral. Okay. So, I don't know how to tell you this one without telling you this one. F of x is equal to, we need a starting point. Well, lucky us, they gave us a starting point when they said that f of 1 equals 3. So, put a 3. You'll see why in a minute. Now, you probably already get it, but 3 is my starting point. And from 3, I will figure out the area. Okay. To go from a derivative to a function, I am finding the accumulated area. Well, I start here at 1, x equals 1, which they gave me the value of that. And then I will accumulate some area. In this case, I'm accumulating negative area. So if I accumulate area, I am doing an integral of my graph. Now, I'm doing this in pieces. My starting point was at x equals 1, and where's it going to go? Well, it's going to go to wherever I tell it to stop. That's x, because I'm evaluating this for x. I can't have an x here and an x here and here. So we'll use f of t dt. You can change variables there. It's perfectly okay. So what this means is the accumulated area from 1 to wherever on this graph plus 3 will tell you the value of the function. So let's think about this logically. If they said, find f of 1, well, it makes sense. 3 plus, and then the area from 1 to 1. The area from 1 to 1 is, well, 0. So it's 3. All right, we have just figured out the function. Now let's actually answer the rest of the question. They said find f of 4. They also said find f of -2. So let's do it. 3 plus the integral from 1 to 4 of f prime of t dt. And this is a graphical thing. So 3 plus, I want to know the area from 1 to 4. Well, the area from 1 to 4 is this, and they told me it was 12. Now, I am moving forward, and this is below the x-axis, so it's -12. So it's 3 plus -12, so -9. Okay? F of -2 is 3 plus, and then the integral from 1 to -2, f prime of t dt equals 3. I'm going to make this plus look more like a plus and less like a t. That's bugging me. There we go. 3 plus, okay, the area from 1 to -2. That's a little backwards. If you want to turn it around and change the sign, you can. I choose not to. If I go from 1 to -2, then I would count this negative as a positive. They told me it was 9. I'm counting it as positive 9 because it would normally be negative if I'm moving this way, but I'm moving this way. So here we go. It's 9. This is 3 plus 9. That's 12. So if you're looking to see what points you can get from this one, here goes. Let's go back to part 1. If you identified x equals 2, or -2, you get a point. And then you needed the justification for it. So there's that. So all that's all one big underline, right? For part B, if you had the correct intervals, that's it. And then your rationale was another point. We've earned 4 points so far. We have 5 more to go. If we identify these x values, 3, -1, and +1, that's another point. And then the rationale is another point. We've earned 6 points. We have 3 more to earn. The integral here is worth a point. The entire expression is worth a point. I kind of take that back. I should have put the box just around that f prime t dt, not the 1 to x. And then you get a point for those 2 answers right there.